Welcome back to the Deep Dive. We love exploring the OEIS, and today's deep dive is into a sequence that might seem simple at first, A000008.
Yeah, it's amazing how much depth you can unpack with this one, A000084. It's a bit like a chameleon, you know?
Yeah. Okay, so for our listeners who haven't encountered this sequence before, what is A000084 counting?
So at its core, A000084 counts the number of possible series parallel networks that you can create with a specific number of unlabeled edges.
Okay.
Think of it like building with Legos. But instead of bricks, you're using edges as building blocks, and you're exploring all the different structures you can create.
So it's the different ways to connect things.
Yeah.
How does that relate to something like electrical circuits?
Well, series parallel networks are the foundation of how circuits are designed. From the simple wiring in your house to a power grid, understanding how to arrange components efficiently is essential.
Right.
And A000084 gives us a mathematical framework for analyzing these arrangements.
So we're talking about more than just like abstract Lego structures. This has real-world implications.
Absolutely.
For how we design and understand electrical systems.
Absolutely. And what's even more fascinating is that AV000084 doesn't stop at circuits.
Oh.
It pops up in graph theory, specifically something called cographs.
Now, I remember from some of our previous deep dives that graphs are all about representing relationships between things.
Right.
What makes a cograph special?
So imagine you're looking at a social network.
Okay.
A cograph helps us model situations where certain connections are either forbidden or imply very specific dynamics.
Okay.
It's like having a social network with rules about who can be connected to whom.
That's you.
And AV000084 helps us understand how many of these unique, rule-abiding networks we can create.
So it's like this one sequence is giving us insights into both the physical world of circuits and the more abstract world of relationships and networks.
Exactly. And that's just scratching the surface. A000084 has even more surprising connections to things like P4 free graphs and the study of equivalent resistances.
Although we're going to need to break that down a bit.
Sure.
What are P4 free graphs, and why should our listeners care about them?
So a P4 is simply a path with 4 vertices.
Okay.
Think of it like 4 dots connected in a straight line.
The way?
A P4 free graph is a graph where you won't find any of these 4-dot paths as what are called induced subgraphs.
Okay, so why is that important? Does avoiding these particular paths have some special significance?
It turns out that P4 free graphs have a lot of interesting properties that make them really useful in areas like computer science.
Okay.
Particularly for things like algorithm design and optimization problems.
So by understanding the properties of P4 free graphs, we can potentially develop more efficient ways to solve complex problems.
Precisely. And the fact that AZ000084 counts these graphs hints at a deeper connection between the way we structure circuits and the mathematical tools we use to solve computational challenges.
Okay, it's already getting my mind spinning. And you mentioned something about equivalent resistances.
Ah, yes. You know how in a circuit you can combine resistors in different ways and still achieve the same overall resistance?
All right, like if you have 2 resistors of the same value, you can connect them in series or in parallel.
Exactly.
And get different results, but with the same overall resistance value.
Exactly. It turns out that A000004 also relates to the number of different combinations of resistors that can produce these equivalent resistances.
So this one sequence, A000084, is popping up in all these unexpected places.
Yeah.
It's like a hidden thread connecting these seemingly disparate areas of mathematics and the physical world.
It really is. And the journey of discovering these connections is what makes exploring the OEIS so fascinating.
Now, I know we can't talk about A000084 without mentioning some of the key figures who've contributed to our understanding of it.
Right.
Where should we start in this mathematical history lesson?
Well, we have to give credit to Percy McMahon, a mathematician from the late 1800s.
Okay.
He was one of the first to really dive into the study of these types of networks, and he came up with a term for them. Yoke chains.
Yoke chains. That's a pretty evocative name. So McMahon was looking at how these networks were structured, how the components connected together.
Precisely. And his work laid the groundwork for how we understand circuit topology today. But there are many more mathematicians who built upon McMahon's foundation, each adding their own insights to the story of A000084.
All right, well, let's delve into those contributions. Before we do, though, I'm curious, is there any connection to A00000804's history and how we are covering it now in this ongoing series on the OEIS?
Well, in a way, yes. Remember, the OEIS itself is a testament to the collaborative nature of mathematical discovery. It brings together the work of countless mathematicians, just like we're doing in this deep dive, highlighting the connections between their findings.
It's a great point. So in a sense, we're following in the footsteps of the OEIS by exploring these connections and bringing them to our listeners. Now let's get back to those other mathematicians who helped shape our understanding of A000084.
We have Oswald Veblen, who introduced some powerful tools from algebraic topology to simplify circuit analysis.
Wait, algebraic topology, that sounds pretty intense. Can you give us a quick rundown of what that even means?
Think of it as a way to study shapes and spaces using algebraic tools.
Okay.
Veblen applied these tools to the study of circuits, introducing concepts like spanning trees, which are essential for understanding how electrical current flows through complex networks.
So Veblen took McMahon's ideas and brought in a whole new level of mathematical sophistication.
Exactly. And then we have Ronald M. Foster, who further refined the classification of these networks, enabling us to analyze even more complex circuits.
It's amazing to see how these ideas built on each other, each a mathematician, adding another layer of understanding to this seemingly simple sequence.
It's a beautiful illustration of how mathematical knowledge progresses. And of course, we can't forget Neil Sloan, the creator of the OEIS itself.
Right, he's the one who brought all these sequences together, creating a treasure trove for mathematicians to explore.
Exactly. And without his work, who knows how long it would have taken for us to uncover all these fascinating connections related to A000084.
So we've got this rich history of mathematical minds, all contributing to our understanding of this sequence. But let's bring it back to our listeners. Why should they care about A000004? What's the takeaway here?
It's all about perspective. If we zoom out and look at the bigger picture, A000084 shows us that even seemingly abstract mathematical concepts can have real-world applications. Whether you're an engineer designing circuits or a computer scientist developing algorithms, this sequence offers a glimpse into the elegance and power of mathematics.
And it reminds us that there's always more to discover, more connections to uncover, even in something as seemingly simple as a sequence of numbers.
Exactly. 000000 is just one example of the countless mathematical treasures waiting to be unearthed in the OEIS.
And we're excited to keep exploring them with you. Stay tuned as we continue our deep dive into A0000C and uncover even more of his hidden connections.
Welcome back to our deep dive into A00000884.
Okay.
Now let's shift gears and explore some of the key research that has illuminated the mysteries of this sequence.
Sounds good to me. I'm ready to see what these mathematical detectives have uncovered.
Well, our journey takes us back to 1942 with John Riordan and Claude Shannon, two pioneers in the field of combinatorics.
Okay.
They published a paper titled The Number of Two-Terminal Series Parallel Networks, which was groundbreaking for our understanding of A000004.
So this was one of the first major works to really tackle the problem of counting these series parallel networks.
Exactly. They provided a fundamental framework for understanding how to enumerate these networks, and their work sparked a wave of further research in the field.
So what were some of the key insights that Riordan and Shannon brought to the table?
Well, their paper delved into the combinatorial aspects of series parallel networks, providing techniques for counting different arrangements based on the number of edges. Think of it like having a toolbox filled with mathematical tools specifically designed to tackle these counting problems.
So they were developing the mathematical language and methods needed to really understand A000084.
Precisely. And then in 1958, Riordan published a book titled An Introduction to Combinatorial Analysis. While not solely focused on A000004, this book provided a broader context and introduced powerful combinatorial techniques that could be applied to the study of series parallel networks.
So Riordan was really laying the foundation for a deeper understanding of how to analyze and count these complex structures.
Exactly. And as the field progressed, other mathematicians started to uncover fascinating connections between A000084 and other areas of mathematics. One such connection emerged in 1987 with a paper by Peter J. Cameron.
Now, I remember from our earlier discussion that A000084 also relates to something called cographs. Was this the connection that Cameron was exploring?
You got it. Cameron's work beautifully demonstrated a link between series parallel networks and these cographs. Remember how we talked about cographs being like social networks with rules?
Right.
Well, Cameron showed that the same mathematical principles underlying A000004 could be used to understand how many different ways we could structure these rule-based networks.
So we're starting to see how A000084 is acting as a bridge between different mathematical concepts, bringing them together in unexpected ways.
It's truly remarkable. And of course, we can't forget the role of Neil Sloan in his creation of the OEIS.
Right. Without the OEIS, it's hard to imagine how we would have even discovered these connections in the first place.
Absolutely. It was in Sloan's 1973 publication, A Handbook of Integer Sequences, that A000084 made its official debut, opening it up to a wider audience of mathematicians.
So the OEIS provided a platform for researchers to share their findings and build upon each other's work. Did this lead to a surge in research on A000084?
It certainly did. We see contributions from mathematicians like Z.A. Lomnicki in 1972 and J.W. Moon in 1987, both of whom delved further into the enumeration of series parallel networks, building upon the foundations laid by Riordan and Shannon.
It's fascinating to think about this global community of mathematicians, each adding their piece to the puzzle, all driven by this one sequence.
It truly highlights the collaborative spirit of mathematical exploration, and this collaborative spirit continued into the 21st century. In 2003, Sloan, along with Eric W. Weisstein, made another significant observation. They noted that A000084 could also be used to count unlabeled cographs, further solidifying the link between these concepts.
So it's like each new discovery strengthens this web of connections, revealing a deeper and more intricate mathematical landscape.
Exactly. And just when you think you've mapped out all the connections, another one pops up. In 2008, Gordon F. Royal added another layer to the story by observing that A000084 also counts what are known as P4 free graphs.
Remember, a P4 is just a path with 4 vertices. A P4 free graph, as its name suggests, is a graph that doesn't contain any of these 4 vertex paths as induced subgraphs.
Right, so we're talking about graphs with certain restrictions on how those vertices can be connected. But why should we care about these P4 free graphs? Well, they have a lot of fascinating properties that make them really useful for things like algorithm design and computer science. Specifically, many algorithms can be made more efficient when applied to P4 free graphs.
So the fact that A000084 counts these graphs suggests a potential link between the efficiency of algorithms and the way we structure circuits.
Precisely. And this connection opens up all sorts of intriguing possibilities for optimizing how we design and analyze complex systems.
Wow, I'm starting to see how even a seemingly simple sequence like A000084 can have far-reaching implications.
It's amazing, isn't it? And the story doesn't end there now. Researchers like Gary W. Adamson and Samin Ahmed Khan continue to uncover connections to other sequences in the OEIS, demonstrating just how deeply embedded A000084 is in the web of mathematical knowledge.
It's mind-boggling to think how much research has been inspired by this one sequence. It must feel like a never-ending treasure hunt for mathematicians.
It really does, and the beauty is that there's always more to discover. Even today, researchers are still exploring the intricacies of A000084, finding new connections and applications.
So for our listeners who are feeling inspired to delve deeper into this world, where would you recommend they start?
The OEIS itself is an incredible resource. You can find A000084 there, along with links to many of the publications we've discussed. There are also fantastic books out there that dive into these topics.
Could you give us some specific examples? I know I'm ready to add some new titles to my reading list.
Absolutely. For those interested in the algorithmic aspects, The Art of Computer Programming by Donald E. Knuth is a classic. And for a deeper dive into the world of graph theory, Graph Classes, A Survey by A. Brandstate, V.B. Lay, and J.P. Spinrad is an excellent resource.
It sounds like there's a wealth of information out there for anyone who wants to follow those threads and explore further.
There certainly is. And remember, exploring the OEIS is like embarking on a grand adventure through the interconnected landscape of mathematics.
And sometimes the most unexpected paths lead to the most rewarding discoveries.
Speaking of discoveries, we have even more fascinating connections and applications to uncover in relation to A000084. Stay tuned for the final part of our deep dive as we delve into even more recent research and explore the ongoing fascination with this remarkable sequence.
Welcome back to the final part of our deep dive into A000084. It's amazing how much ground we've covered, from simple circuits to complex graphs and algorithms.
Yeah, it really highlights how interconnected different areas of mathematics can be. And we still have more fascinating connections to explore with A000084.
I'm all ears. Where do we go next on this mathematical treasure hunt?
Well, let's jump into the world of equivalent resistances. Remember how we talked about different combinations of resistors that can produce the same overall resistance in a circuit?
Yes. It was fascinating to think about how those different arrangements could lead to the same outcome.
Well, a researcher named Antoni Amengwal explored this concept in depth back in 2000.
Okay.
His work shed light on the mathematical underpinnings of equivalent resistances and showed how A000084 plays a role in understanding these different combinations.
Okay, I'm trying to picture this. How does the number of series parallel networks actually relate to those different resistor arrangements?
Think of it this way. Each series parallel network represents a unique way to arrange resistors, and A000084 tells us how many of these unique arrangements are possible with a given number of resistors. Some of these arrangements, even though they look different, will result in the same overall resistance.
Ah, I see. So A000084 is like a master key that unlocks the different ways we can achieve equivalent resistances in a circuit.
Exactly. And this connection between A000084 and equivalent resistances continued to intrigue researchers. In 2010, Samin Ahmed Khan explored how A000084 relates to other sequences in the OEIS, specifically A1FEN 6500 and A16 and 6502, which delves even further into the intricacies of equivalent resistances.
So it's like we're peeling back the layers of an onion, revealing more and more complexity with each new connection we uncover.
That's a great analogy. And these connections extend beyond circuits and resistors. Remember how we talked about A000084 counting cographs, those special types of graph that can model things like social networks with rules?
Yes. It was fascinating to see how this sequence bridged the gap between those abstract networks and the physical world of circuits.
Well, Michael Somos made a fascinating observation about A000084 in 2006.
Oh,
He found that it also counts the number of elements with a specific number of occurrences of a generator within a certain algebraic system.
okay. I have to admit that sounds a bit abstract. Can you break it down for me?
Think of it like a mathematical language with its own set of rules for combining symbols. You have a starting symbol, your generator, and A000084 counts how many different sentences you can create in this language using a specific number of those generators.
So it's like A000084 is revealing patterns in the way we construct these mathematical expressions.
Precisely. And it shows how this sequence extends beyond just circuits and graphs into the realm of abstract algebra.
It's amazing how A000084 seems to touch on so many different branches of mathematics.
It really speaks to the interconnected nature of mathematical knowledge, and the discoveries didn't stop there. In 2012, researchers Takehiki Uno, Ryuhei Ohara, and Shinichi Nakano published a paper that tied together several concepts we've discussed.
Oh, which ones were they connecting?
Their research explored the relationship between A000084, something called reduced trees, cographs, and series parallel graphs, demonstrating how this sequence acts as a common thread, weaving together these seemingly disparate areas of graph theory.
It's like A000084 is a roadmap guiding us through the interconnected landscape of mathematics.
That's a great way to put it. And this exploration is far from over. Even today, researchers are still uncovering new connections and applications for A000084.
It's inspiring to think about all the possibilities that still await discovery within the OEIS.
Absolutely. It's a treasure trove of mathematical insights waiting to be unearthed. And we hope this deep dive has sparked your curiosity to explore further.
We've covered a lot of ground from the history of A000084 to its surprising connections across different areas of mathematics. What's the key takeaway you want our listeners to remember?
If there's one thing to take away from this deep dive, it's that even seemingly simple mathematical concepts can have far-reaching implications. A000084 might just be a sequence of numbers, but it's opened up a world of connections revealing the elegance, power, and interconnected nature of mathematics.
So whether you're an engineer, a computer scientist, or just someone who loves exploring the beauty of mathematics, A000084 offers a glimpse into the magic that happens when we start connecting the dots. Thanks for joining us on this deep dive. We'll see you next time as we continue our exploration of the amazing world of the OEIS.